Yeah.
Yes.
Anyhow, I'll leave the link on the slides if you guys want to look at it later. Just need to move on here a bit. So I want to do an example, in calculating the electric field from the potential for the case of a point charge. And we want to do this in Cartesian coordinates. Life is a little easier. You don't have to worry about the Jacobian, converting from Cartesian to spherical. I don't know if you're familiar with the word Jacobian, but someday you will. But it's just you have to take into account that when you're transforming into different coordinates that are not really linear respect to each other, you have to take that into account in terms of like angle theta, phi, that's used in the like zenith and the azimuth for the spherical coordinates. So I think the simplest thing to do this, ideally it'd be best to do this in spherical. I wanted to do it in Cartesian.
Excuse me, Professor.
Yeah.
Can you explain again why we had to convert a scalar into a vector quantity using the gradient operator? I was kind of confused.
Let's say the case that you do not. I mean, you're working on some project, doing some measurements, and it's just you just don't have a device to measure the electric field, but you do have a device that measures the potential. Okay, so you have this map of the potential, everywhere in space, close by to whatever object that you're working on. And then once you have that mapped out, then you can determine the electric field from that.
So it's really just for the use of converting a potential to an electric field. Well,
it's related. I mean, we did the calculation going from electric field to potential. I mean, it should be obvious. I think that we should be able to do the opposites. But what I'm saying is that there's some situations as an engineer, you may not have all the information you need. And so you may be giving some information, but from that, you might be able to extract, what is needed to do your project, for example. I think it's just important to be able to see that, basically the gradient represents the steepest descent in a potential gradient, or potential scalar field. Okay, so what we have here is a point charge. It's located at the origin. We have X, Y, Z coordinate system already drawn here. And I just put some numbers on the various equal potential lines. Let's say 50 volts, 40, 30, 20, 100, 10. It's spaced out about what you would expect, in terms of like 1 over R. 10, but if you think of 10 is here, about half the distance should be 20, and that's about what you see, and so forth. So first, what we want to do is convert. We want to just replace R with Cartesian coordinates which we're showing here. So we have KQ divided by square root of x squared plus y squared plus z squared. And so now what we want to do is apply the gradient operation onto this potential and see what happens. So that's what we'll do. So if we take the partial respect to x onto the function which describes the electric potential, we get the following relationship. You guys see how I went from that step? Just taking this function on the top page on the right.
I think that it would help for people who haven't learned their partial derivatives yet in math to go through how you took the partial derivative with respect to x there.
Well, in this case, I don't think it really makes a difference where it's implicit or explicit, because it doesn't show that x and z depend on y and z does depend on x. So we're just taking a derivative. Just ignore that this is a partial. This is just d v dx. We're just taking a derivative. We're taking a derivative of this function. All right. So by doing so, remember this is the same. This is raising this part to the 1/2 power. So by taking a derivative of this, it becomes to the 3/2 power, right? And then take the derivative on the inside. So I'm assuming you guys are familiar with the chain rule, right? And taking derivatives.
Yeah.
Yeah.
I think that was introduced in 241. And you guys have seen derivatives like this, right?
Yes, that's
Yeah, that's okay. All right. So we can rewrite this then in the following manner. This is the x component. It's minus k cubed for r. I mean, basically you can say, well, you know, this is basically r cubed. All I did here is I factored out r. You guys see this term here is the same thing as r cubed? I hope.
Yeah, I see it.
Okay. So all I did was factored out a r, factored out the x, and this is basically the x projection. You can think of it that way. But it just comes out naturally by doing this operation, by doing this derivative, seeing how much does the this electric potential change in the x direction.
I'm sorry, what was your reason for factoring those two out again?
What's the reason of taking a derivative with respect to x?
No, what was your reason for factoring out 1x?
Oh, well, the main reason here is, since we're looking at, if you think about it here, this derivative with respect to x, which will give us the x component of E. You remember electric field kind of goes as 1/r², if you remember that? And if you want the x component of that magnitude, then you take the projection onto the x-axis, and that's basically what this part is here. This is the projection onto the x-axis, the magnitude.
So you took the derivative of like k with q over the square root of x squared plus y squared plus z squared and did like the derivative with respect to x?
That's all it is. If you take this function here on the top right, and take the derivative with respect to x, that's all I'm doing.
So the v equals k and then q over the square root of x squared plus y squared plus z squared?
This is that's what I'm taking a derivative of. This is what the electric potential function, how it's defined.
Yeah, I understand how you get like the bottom, but when you're taking so you said it was the chain rule, so I was trying to run through that and do it.
Yeah, the
And
chain
that-
rule, basically, what you do is first take the derivative. You have some term that includes the dependence, whatever differentiation that you're taking. In this case, is x.
Yeah.
So the whole term, you just treat that as like a separate, I don't know. He's treated as like, is it a function of his own, and then you say, well, okay, it's raised to like the nth power. When you take the derivative of that function, it goes to the n-1 power times the derivative on the inside of that term. And the derivative on the inside is just 2x.
Yeah. So my question is, I was doing it and I got the bottom, which is x squared plus y squared plus z squared. But I got on the chain rule, wouldn't it be 2x, or shouldn't the top of it be 2x?
Oh, but don't forget that you look at this function in the denominator, the x squared plus y squared plus z squared, that has you're raising that power to a half, right?
Yeah.
So you bring that half out when you take the derivative. Remember, for instance, like x.
Oh, I see it now.
So that's the 2's cancel is one.
Okay.
Okay.
All right, I see it now. Thank
All
you.
right, yeah. Sorry, I should have did a little more steps in this. Well, I think it should be obvious that the X and Y, I mean, the Y and Z part should be very similar, except we're projecting onto the Y axis and the Z axis. So we should have these forms for the Y component and the X component. Is everybody convinced of that?
Yes, because the
If
derivative.
anybody's not convinced, I guess is the
Same
right word.
variable.
All right, well, let's just go on then. Taking that information, it's basically now it's in this table. And so what I want to do is make the substitution for each of these parts. So in other words, the derivative with respect to X is this part. The derivative with respect to Y is the middle part, minus KQ divided by R squared times Y over R. And for the Z, same except that you have a Z as opposed to a Y in the numerator. Okay, so I'm just going to substitute that in. And let's see what we got. Okay. Now what I want to do, I want to factor out KQ over R squared. You can see us common in every term here. But I'm going to leave the 1 over R's there. You'll see why in a moment. And this is basically your R hat. This is the vector, the radial vector, the unit radial vector in Cartesian coordinates here. And so, that being said, we're back to where we started. Sort of, I mean, which is good. So, I mean, if you're in a situation where all you have is, the ability to measure, the electric potential, well, this is a way to get the electric field if that is what you need, or vice versa. So you did have a, table of electric field measurements. Well, from that, you should be able to extract out the potential if that's what you need. You need one or the other, though. I suppose if you knew the charge distribution at some location, then you could determine both electric field and potential from that charge distribution. All right. I think this is it's pretty useful. Just to make a point here is how the electric field is related. I mean, it's related to how fast the potential is changing in this case. And if we were to look in this case, if you had a uniform electric field, this is it's parallel plate or parallel charges, and in this case, let's make the assumption that this is an infinite plane in this case, and consequently, your electric field should come off perpendicular to the surface everywhere. Whoops, sorry. And so if you were to to calculate, the electric field is constant everywhere, you can just pull that out, and it's basically the change of potential is just a function of your path, how far you're away from one plate to the other. But
I have a question.
sure.
So you have obviously information there related to delta V. Is that different than, I don't really know how else to describe it, the delta that was upside down, the upside down?
Oh, yeah. This
earlier?
is, the upside down delta is almost, I think it's distinctive in that it's only used in the case for, this gradient operator. And this represents the difference. If you see a delta, right side up delta, it usually just means a difference from one point to another, are evaluating potential one place compared to that to the other. So no, this is it's unrelated to that.
Okay.
Well, yeah, fair to say it is. So anyhow, this is a pretty simple case, but I just wanted to make this point. This is a really good way to relate these two together. This gives you an idea, how fast one is changing versus the other. All right, I want to move to, we already looked at some cases. Well, I think we just actually, the first example we did in terms of calculating electric potential is from the Van de Graaff, and then made the assumption that the Van de Graaff is a perfectly perfectly shaped sphere. And now what I want to look at is determining the potential for a dipole. And nature likes dipoles. I mean, so many molecules out there that you wouldn't think there would be dipoles, but it's just the way they're oriented. For instance, in the case with H2O, water, you have hydrogen, and then you have oxygen bonding those two together. And if those were in a straight line, for example, physically, the dipole would be zero. But in fact, they're rotated a bit, and as a result of this rotation, I guess this way to describe it's like Mickey Mouse ears. You do have a dipole moment, but nature tends to like dipoles, and we'll get into this a little further later in capacitance. I just thought we'd just go through the derivation. It's using a superposition. I mean, it's valid in most cases, all cases I'm aware of, for electric fields as well as potentials. So we'll apply the superposition method to an electric dipole. In this case, you see here on the far right in our diagram. So they're on the z-axis in a vertical direction. They're separated by distance d. O represents where z equals 0. I guess you could project a y or z horizontally. It's a little relevant moment, I guess, but this is assumed now that if you project over to the right, the horizontal axis, that's x. And our observation point, P, is some distance away, R from the from the origin. But of course, what we need is the distance from each charge, plus q and minus q, which are d divided by 2 distance away from the origin. And this is how I derive what I'm calling the plus radius, which is from the plus charge, and the minus radius. I don't know if radius is the right word. Is a distance, I guess, away from that negative charge is given by this relationship here. Okay. All right. So in the case, each charge produces a potential. It's called V plus and V minus. And those can be simply added together. I mean, really added, not vectorially. Being that this is a scalar field, we don't have to worry about direction. This is kind of the nicety about dealing with potential. So the net potential is just the rhythmic sum of the potential produced by the positive charge and then that produced by the negative charge, which is this. I mean, this is the relationship of potential for a point charge. You guys understand why there's a negative sign here, right? Because it's a negative charge. And this is a positive charge. Okay. I think the silence is a yes. So if we were to substitute in for R sub plus and R sub minus, we'd have this. Looks a little complicated. simplify it a little bit, but I just wanted to show what this looks like. If you were to draw the equal potential lines, and these are equal potential lines are blue. You can see an interesting thing is that as you get closer and closer to each charge, you can begin to ignore the other charge. It begins to look more spherically symmetric. And it's no surprise there, being that this is 1/r relationship between the potential and this distance away from the charge. But as you get away, you can start to see this distortion a bit. And the electric field is also shown in red. And you can see everywhere the electric field is perpendicular to the equal potential lines. Now, one thing I wanted to show in this, I think it's important, it's just all I did here is I rotated the dipole such that now the plus is on the right, negative is on the left. This gave some numbers for the potential surfaces or potential lines. But the thing I wanted to show here that, although the potential is the same everywhere, let's just take this outer blue line, blue circle, semicircle, it's more like an ellipse, I suppose. Is the electric field the same everywhere on this electric potential? My question to you.
No.
Doesn't look like it, does it?
No.
It certainly would be the case if there was a single charge in space. But due to this distortion, you can see the field, there's more field lines on the the right-hand side than on the left. So in general, that's not the case for all points on an equal potential. The electric field could vary. I mean, there's exceptions to this, and in the case for you had a sphere. I mean, I'm sorry, not a sphere, but if you see this, but happy birthday balloon, it's nearly spherical. But the thing is, if you had a charge in the middle, and this charge is the only charge in the universe, let's say.